Imagine watching your cloud compute budget just evaporate in real time, simply because your foundation model is trying to process a 10-second video clip.
Oh yeah, the dreaded token explosion problem.
Exactly. I mean, it has been the biggest bottleneck for literally anyone building multimodal architectures today.
It really has.
Welcome to AI Paperslop, where we bring you the latest research straight from the source. Today, we are jumping right into a paper called VideoChat3, Fully Open Video MLLM for Efficient and Generalist Video Understanding.
And this one is from an absolute powerhouse collaboration. You've got researchers from Nanjing University, the Shanghai AI Lab, NTU, and Peking University.
Right. So look, if you are an ML engineer dealing with the absolute nightmare of video data scaling, here is your bottom line. VideoChat3 is a 4 billion parameter multimodal large language model that finally solves the video encoding bottleneck.
Yeah, and it does that by compressing the spatiotemporal data before it ever even hits the LLM.
Exactly. It relies on this inflated 3D vision transformer and adaptive frame resolution to hit state-of-the-art performance.
Yeah.
And that's across short, long, and streaming video.
Which is huge, but...
And that exponential growth kind of exposes this illusion of video understanding in current open source models, doesn't it? Like the standard architecture for a video MLM today doesn't actually understand motion at all.
No, not natively. The visual tokenizer they use is almost always just a repurposed image tokenizer.
Right. It just sparsely samples the video, maybe pulling like one frame every second, and then it runs each of those frames through the tokenizer as an isolated, completely independent image.
What's fascinating here is that the spatial encoding happens in complete temporal isolation. So the tokenizer figures out, okay, there's a dog in frame 1 and a dog in frame 2.
But it doesn't know it's the same dog.
Exactly. It has no structural mechanism to understand that it is the same dog moving across a field. The model refers all that temporal modeling, all the heavy lifting of understanding motion and causality, straight to the LLM itself.
Which means all those raw visual tokens are just, dumped into the language model's context window.
Yeah, forcing the LLM to figure out the physics of time on its own.
Which is such a wildly inefficient way to process information. I mean, treating a video like a stack of independent Polaroids completely ignores how motion works. It's like trying to understand a dance by looking at a slideshow.
That is a perfect analogy, and you miss all the subtle transitions.
But the real problem for an ML engineer isn't just the lost information. It's the sheer volume of redundant garbage being fed into the network.
Oh, absolutely.
Think about it. If you have a 10-second clip of a person sitting at a desk talking, the desk, the lighting, the background wall, it's completely identical across every single frame.
But the image tokenizer doesn't know that. It meticulously encodes the pixels of that background wall for frame 1, generating a sequence of tokens.
Right.
Then it re-encodes the exact same wall for frame 2, generating the exact same tokens all over again.
So you just get this massive influx of visually identical tokens.
Highly redundant tokens, yeah. And when those finally hit the LLM, the attention mechanism burns through literally billions of calculations just to figure out that a coffee cup in the background hasn't moved.
It's insane.
Yeah.
And that computational waste is the direct cause of the generalization problem we see right now. Processing those tokens is so expensive that researchers are basically forced to specialize their models just to survive the compute constraints.
Yeah, you end up with a model that performs brilliantly on like a 5-second action clip. But if you feed it a 2-hour movie...
It runs out of memory and just crashes.
Right. Or if you try to use it for real-time streaming, it stutters and fails because it just cannot process the incoming frames fast enough to generate a response.
So this is where VideoChat3 comes in, right?
Mm-hmm.
It introduces a paradigm shift by relocating that burden of temporal modeling.
Yes. Instead of passing a mountain of raw, isolated image tokens to the LLM, VideoChat3 forces the visual tokenizer itself to understand time.
Okay, let's unpack this hardware-level compression, because the paper details 2 distinct strategies here, temporal compression and spatial compression.
Right, let's start with temporal. They deploy what they call an inflated 3D vision transformer, or I3D VIT.
And the concept of inflation here is super interesting, because they aren't just training a 3D transformer from scratch, are they?
No, because that would take an astronomical amount of data and compute. Instead, they start with a standard, highly optimized 2D spatial vision transformer that has already been pre-trained on millions of static images.
So it already knows what things look like.
Exactly. The mathematical inflation involves expanding those 2D spatial self-attention blocks to include a third dimension, which is time.
So it leverages all that rich spatial understanding about shapes and textures, but now can track how they change across a temporal sequence.
Precisely. And to make that work without blowing up the memory, the model doesn't just look at the whole video at once. It partitions the video into contiguous chunks.
Okay, so let's say a chunk is a group of up to t consecutive frames.
Right. And inside that specific chunk, the model obviously needs a way to track the order of events. So it applies learned absolute temporal embeddings to the frame indices.
Like little timestamps stamped onto the tokens.
Yeah, exactly like timestamps. This gives the transformer an explicit understanding of the sequence, so it knows which frame came first, second, and third within that specific chunk.
Got it. And then all the tokens from the frames in that chunk are flattened into a single sequence?
Yes, allowing the ViT blocks to perform joint attention over space and time simultaneously right at the native input resolution.
So the neighboring frames are finally interacting with each other inside the tokenizer itself. The visual encoder's actually seeing the motion.
It is, and that sets up the most critical efficiency mechanism in the whole paper, chunk-wise temporal pooling.
Okay, break that down for us.
So after the spatiotemporal attention layers have contextualized all the tokens, identifying the motion and recognizing the static background elements, the model aggregates those features along the temporal dimension.
So if your chunk has T frames,
the pooling mechanism mathematically collapses those T-frame representations down into a single representation. You reduce the total token count by a factor of T.
oh wow. So you effectively summarize the local motion and just strip out all that redundant background data.
Exactly. The LLM receives just a fraction of the tokens it normally would, but those tokens now contain dense spatiotemporal meaning.
That is brilliant. It completely solves the temporal bottleneck, but they also tackle spatial compression, right? Specifically for real-time streaming using adaptive frame resolution.
Yeah, this is where the model dynamically adjusts the spatial resolution of incoming frames based on how important it thinks they are.
Okay, wait, let me play devil's advocate here. Because dynamically dropping resolution on a live feed sounds incredibly risky for a computer vision model.
How so?
Well, if the model is processing a low-res feed to save compute, how does it know when something important is happening? Like, it seems guaranteed to miss the exact high-fidelity detail it needs to identify a critical event.
It sounds risky, sure, but that's precisely why they base this mechanism on biological principles. Human vision operates on a very similar resource allocation model.
Oh, really?
Yeah. Think about when you're staring at a static, predictable scene, like an empty hallway. Your visual cortex processes that scene coarsely. You aren't analyzing every pixel of the wallpaper.
True.
But the moment something unexpected happens, say, a door handle starts turning, your brain triggers a saccade. It snaps your focus, your fovea, onto that specific area for high-resolution, fine-grained perception.
So the model is literally mimicking the pacing of human visual attention. It saves the pixel budget for when it actually matters.
Exactly. The architecture maintains a very cheap, low-resolution processing baseline during those uninformative, static intervals. It's just scanning this low-res feed, looking for semantic triggers that indicate a state transition.
And when it sees one.
When the visual evidence suggests an action is beginning or a new object enters the frame, the model actively decides to allocate its pixel budget. It pulls in the incoming frames at a much higher resolution, getting those fine-grained details only when the context demands it.
That is such dynamic, intelligent resource allocation. But, an elegant architecture is really only half the battle here.
Oh, for sure. Data is the other half.
Right. Because in machine learning, a highly efficient engine is completely useless if you feed it garbage fuel.
Yeah.
If you train this inflated 3D transformer on standard, low-quality video captions, it's never going to learn those complex causal relationships.
The data bottleneck is arguably just as critical as the compute bottleneck.
So to fix this, the team built a data synthesis engine. They curated a massive 3 million sample training pipeline broken down into 3 targeted datasets.
Yeah. You've got VideoChat3 Academic 2M for general understanding, LV116K for long-form video, and OL617K for online streaming.
Let's start with Academic 2M, because their methodology here is basically a masterclass in how to not screw up synthetic data.
Right. They used a pipeline called evidence-grounded annotation enhancement, because the problem with traditional academic datasets is that the ground truth annotations are usually incredibly dry. They're sparse and uninformative.
Dog runs. Right.
Exactly. So the obvious solution everyone tries is using a powerful visual language model to rewrite those sparse labels into dense, highly detailed explanations.
But that powerful generator model is naturally prone to hallucination.
Very much so.
It might look at that video of dog running and write this beautifully fluent paragraph about the dog running through a field of daisies, even if there are literally 0 daisies in the video.
And if you feed those fluent hallucinations back into your foundational training set, you just silently poison the reliability of the whole model. It actually learns to invent details.
So how do they stop that?
To prevent the degradation, they put in a strict automated verification stage. They deployed Qwen3 VL235B, which is a massive 235 billion parameter multimodal model exclusively as a judge.
Oh, I love this. The 235 billion parameter model is basically acting as a bouncer at the door of the dataset, checking IDs.
That's exactly what it is. Its only job is to compare the newly generated enhanced response against the original sparse annotation. It strictly enforces semantic consistency.
So it's looking to see if the new explanation changes the core meaning or contradicts facts.
Right, or if it overspecifies details that just aren't supported by the original label. If the enhancement violates that boundary, the judge rejects it outright.
Why? So the original academic label remains the absolute boundary of truth, and the rewrite just provides a richer linguistic expression of that exact truth.
Yes. If we connect this to the bigger picture, this is the blueprint for scaling synthetic data without destroying your academic baseline reliability.
That is so smart. Okay, moving from short clips to the long video dataset LV116K. This introduces a totally different structural problem because these videos average anywhere from 156 seconds up to like 1,300 seconds.
Yeah, that's a massive jump in context.
And current annotator models have strict context window limits. You cannot just shove a noisy 20-minute video file into an annotator and expect a perfect chronological summary.
No, the temporal span is way too wide. The visual information is too dense, so the annotator will inevitably lose track of events or just start hallucinating connections.
So here is where it gets really interesting. They aren't just shoving a 20-minute video into an annotator. They're basically building a timeline ledger of events.
Right, using a technique called boundary-aware temporal segmentation via Piscine detect.
So instead of treating the video as one massive block, they use Piscine detect to analyze the visual feed and actually detect the shot transitions and scene changes.
They systematically break the video down into visually coherent temporal segments, and by enforcing minimum and maximum duration constraints on these segments, they hit a structural sweet spot.
Meaning they don't let the segments get too short and lose context, but they also ensure no segment is too long for the annotator to describe perfectly.
Exactly. Each bite-sized segment is annotated individually with really high precision, and then they assemble all of those segment-level annotations into a structured timeline ledger for the entire video.
So it's an event log mapped directly to the timestamps.
Yes. And building that validated evidence ledger fundamentally changes how the final model learns to reason over long horizons.
Because if something critical happens at minute 2, and then it's relevant again at minute 18, the model usually struggles to connect those dots across all that noise.
Right. But with the boundary-aware temporal segmentation, the supervision is structurally anchored to the timeline. It explicitly teaches the model exact temporal localization and long-range causality.
That makes so much sense. And speaking of causality, we have to talk about the final dataset, OL617K. This one has over 617,000 instances designed specifically for online streaming.
Which is a whole different beast. Real-time understanding means the model is processing a live feed. It literally cannot look ahead to the end of the video because the future hasn't been recorded yet.
Right, so the OL617K dataset forces the model to make predictions based solely on the accumulation of visual evidence up to the current frame.
It trains it to maintain context over short and long horizons without the luxury of knowing how the story ends. It's pure causal streaming context.
Okay, so we have the highly efficient engine with i3D VIT, and we have 3 million samples of high-octane fuel. But how do you train it without destroying the pre-trained weights?
Yeah, you can't just dump this massive dataset into the uninitialized network all at once. The huge influx of gradient updates would completely destroy the delicate spatial understanding the vision transformer originally learned.
You'd induce catastrophic forgetting.
Exactly. So avoiding that requires a multi-stage curriculum learning approach. They ease the architecture into its new capabilities using a 2-stage process.
Stage 1 is the projector warm-up.
Right. During this phase, they completely freeze the weights of both the vision transformer and the large language model. The only thing being updated is the projector module.
which is just the architectural bridge connecting the visual encoder to the language space.
Yes. They train that isolated projector on about 1.04 million image and video caption pairs. And by freezing the VIT, its pristine spatial perception remains totally intact.
The projector just learns the mathematical mapping to translate visual features into a format the LLM can read.
It solves the alignment problem without causing representation drift. Then, once the bridge is stable, they move to stage 2, full parameter fine-tuning.
And this is where they unfreeze everything.
Unfreeze the VIT, the projector, and the LLM, and train the entire system jointly on the massive 3 million sample dataset. This is where the inflated vision transformer finally adapts its weights.
Evolving from a static, image-centric encoder into a dynamic, spatiotemporal video representation. And honestly, the benchmark results proving the success of this curriculum are just staggering.
They really are, especially considering VideoChat3 is only a 4 billion parameter model.
Yeah, it systematically surpasses prior open-source models that have equal or significantly larger parameter counts, like Qwen3VL4B and Malmo2-4B.
The gains are massive across temporal perception, long video reasoning, and online streaming. It just dominates benchmarks like Motion Bench, TempCompass, VideoME, and LV Bench.
And for you ML practitioners out there dissecting the paper, you have to look at tables 7 and 8, the ablation studies.
Oh, the ablations are the definitive proof that the data synthesis pipeline is the mechanical cause of this performance.
Right, because they evaluated a variant of the model trained exclusively on raw standard annotations and compared it against the one trained on the academic 2M pipeline.
And the enhanced dataset produced massive quantifiable leaps in temporal grounding. They ran the exact same ablation for the long video pipeline, which proved that the boundary-aware segmentation directly resulted in the superior long-range reasoning.
The rigorous data curation directly scales the model's intelligence.
Oh.
So what does this all mean for you? If you are building agentic workflows or complex video perception systems right now, this paper changes the landscape.
It really lowers the compute barrier to entry for real-world video modeling.
You finally have a fully reproducible 4 billion parameter foundation model that can actually fit on reasonable hardware. And the fact that they open source the weights, the code, the training strategies, and the data sets is a massive acceleration for the community.
It's huge. The chunk-wise pooling solves the token bottleneck. And the synthetic data pipelines prove that meticulous curation can punch far above its weight class.
Absolutely.
But, looking closely at the streaming capabilities, specifically how they structured the OL617K dataset, reveals a much larger implication for where this technology is heading.
What do you mean?
Well, they trained the streaming model using specific state transition tokens: silence, standby, and response.
Okay.
The model is continuously evaluating the live video feed and making an autonomous frame-by-frame decision. It looks at the visual evidence and decides, do I remain silent? Do I stay on standby because an action is currently unfolding and I need more context?
Or has the semantic event concluded, giving me enough information to interrupt and respond?
Exactly. If a compact 4 billion parameter model can dynamically manage its own pixel budget by dropping resolution when a room is empty and actively decide when to wait for more evidence versus when to act.
We aren't just looking at video analysis anymore.
No, we are looking at the foundational sensory architecture for real-time physical world autonomous agents.
That is wild to think about. How will you integrate this kind of dynamic real-time visual pacing into your next agentic workflow? Something to definitely chew on. That's all for today's deep dive into the material. Thanks for joining us on AI Paper Slop, and we'll see you next time.